Alright, so the scientific method, you're all upperclassmen by now, you've taken a lot of prereqs to get here. Hopefully you have a pretty good understanding of the scientific method. So I'm not going to spend a lot of information or a lot of detail on this, we're just going to kind of blow through it. But basically, you have an observation, probably repeated observation, you've seen this happen over and over and over. From that, you come up with a hypothesis, you test that hypothesis, and then it either supports or doesn't support your hypothesis. The data doesn't. If it does support it, cool. Disseminate those findings, write it up, send it out, tell somebody, and then make additional predictions. If it doesn't, come up with a new hypothesis, right? So your hypothesis has to be testable. It has to be something you can test, and it potentially explains a repeated observation. And we normally do this in a set of two. So you have a hypothesis and the null hypothesis. When we're doing stats, we are normally checking this null hypothesis. So you come up with an idea, and then basically a null, which is like, okay, it's either this or not that. Let's see. An example would be like, I don't know, you come out every day and there's fresh poop in your yard. You'd be like, I think my neighbor's dog is pooping in my yard. That's your hypothesis. The neighbor's dog is pooping in your yard. Your null hypothesis is not the neighbor's dog pooping in your yard. Okay? So it needs to be testable. So how are you going to test it? You need to be able to repeat it. So test it once, test it again. In science, there's not, at least in scientific publishing, there's not a lot of publishable repeated experiments. They really focus on the novelty of stuff. So I think that's somewhere where we're like dropping the ball a little bit, because it needs to be tested multiple times for this to be validated, for us to be like, hey, yeah, this is true. It needs to be, or have replication. It needs to be able to be replicated, which means you can do it multiple times and you get a similar result. So if you repeat it and you get a completely different result, something's up, right? That means your experiment is not testing the right thing, or there's some variation in there that you weren't expecting. Something's going on. There needs to be randomization whenever that's possible. So if you're testing individuals, you can be like, individual A can either be in group 1 or group 2. There's no skewing which group A gets put into. It's either 1 or 2, right? Like a flip of the coin. How we test these hypotheses, there's a lot of different ways to do it. One, and probably the most common, is using a manipulative experiment, where you take you take a variable and then you change it to see if it is what is influencing your thing. So here we can see this spider, this argiope, puts in this thing called a stabilitum. It's just like a little zigzag. We see that in a lot of these orb weavers, where they put in this stabilizing mechanism. You can test the hypothesis that this mechanism is put in so birds don't run into the spider's web. You can do that by having spider webs with or without the stabilium and see what happens. If more birds run into the ones without, cool. You have validated that hypothesis. You can also do microcosm experiments, where you make little bitty worlds. Here's one with algae. Dr. Puneet Singh does this a lot in his lab with Daphnia. I think Dr. Andy Jalowski does it too, where they make these little microcosms where they can put stuff in to see how that influences the algae and the Daphnia and whatever else is going on. So like micrometals, or more phosphorus, more nitrogen, more whatever. See how that changes how these organisms respond to that environment. You can do larger natural experiments. With natural experiments, it's going to rely on natural variation in the environment itself. So an example would be a large island has more diversity. Well, you can check the diversity on this island versus these smaller islands and see if there's a correlation. And then you can be like, oh, second hypothesis is they have more diversity because they have various climates. So there's more climates on this island versus these islands. And so, like, you can build your hypotheses like that. Or something that's really big in ecology is using mathematical models. So using a system with set equations to go with a hypothesis. And then you can test that against the real world to see if that's something you see. So, like, testing population size using births, deaths, immigrations to see what happens to that population. And you can plot curves like this or whatever. Alright, so you do these experiments and you get the data. What do you do with the data after you get it? You've got to analyze it, right? You have to do some sort of stats to let you know that what you found is true or not true. So we calculate the means and the variances, because just using the means cannot tell you the whole story. So if we look at this group, we see group A, group B, they both have the exact same mean. But when you look at the ranges, there's a lot of variation to the range. So in this one we have 8 to 12, this one we have 5 to 15. So the range in group B is much larger than the range in group A. So this, what does this tell you about the means in each of these groups? So the mean for group A is pretty similar to what you're going to find in the population. So it's a better representation of the average individual in that population versus group B. The average individual in group B isn't really representative of a lot of the people in the population or individuals in the population, because that population has such a wide range that it doesn't really help you so much as identifying that. And so we also calculate the variances to tell us how close is the mean to the population. And you do that with this nice little equation here. So you can check the variance of the mean. This is when you look at how that mean and the data spread around that mean of the population, how close is the mean to the rest of the individuals. Yeah, we'll just move on. So what you do is you square each observed value, calculate the mean of these squared values, and then from this subtract the square mean. Lots of words. We'll run through an example in a little bit, just to show you how it works. Rarely do we have the entire population where we can find the mean of this population and then do the variances of the entire population. Doesn't really happen. Instead, we use sample means and do sample variance. So we're saying from our data set, from this group that we have analyzed, here is the mean, here's the variance. But we're not saying this is it for the entire population, it's just for our sample. So your sample variance is just for your sample of that population. Bigger the sample size, the more explanation, or the closer it's going to be to what's true in the population. And so it's important to take a large sample so it can be more representative of that population, but sometimes you just can't. So here's our example, real quick. We have two groups, caged trees, uncaged trees. And we're measuring, I don't even know what we're measuring. Let's say we're measuring leaves. And in the caged trees, we find we have 8, 6, 7, 9, and 5 leaves on each one of these trees. On the uncaged, you have 4, 3, 2, 4, and 2. So if we want to find the mean of your caged trees, you add them up, divide by the number of samples, which is 5, and you get 7. And then to figure out the mean squared, you're going to go 8 squared plus 6 squared plus 7 squared plus 9 squared plus 5 squared, and then you're going to divide that by the n, or the number of individuals you have, which is still 5, and you get 51. And then we plug that into this equation, right, to get your S squared, or your variance. And so here we have n, which is 5. It's how many individuals we have. Below that you have n minus 1, which is 4. And so you have 5 over 4, which comes out to be 1.25. As your sample size goes up, what's going to happen to that number? It's going to get closer to 1, right? And then we take our squared mean minus our mean squared to get your variance. Alright, so 51 is what we got right here. And then you take your mean, which is 7, and square that. It gives you 49. And then you're going to multiply that by your sample of 1.25 to give you 2.25. Now I want you to do this with the uncaged trees. So 4 plus 3 plus 2 plus 4 plus 2. What is the mean of that? Should be something like 3. And then 4 squared plus 3 squared plus 2 squared plus 4 squared plus 2 squared divided by 5. You should get something close to like 9.4-ish. And then plug them in and see what you get. I think it's going to be pretty close to 8. Alright, so explain the scientific method. What do we do? Why do we do it? You gotta observe something repeated multiple times, come up with a hypothesis, something that is testable and can also be repeated multiple times, get your data, validate your hypothesis, or accept or reject your hypothesis based on the data, and then move on from there, right? In what ways do manipulative experiments differ from natural experiments? What's the big difference between those two? And with that, we're done with Chapter 1.